Okay guys, in this lecture I want to talk about capacitors. This is the last thing in chapter 2, so the reading is the last section, 2.5.4, and then we're going to move on to chapter 3. Stuff's going to get a little bit more complicated, but it's going to be fun. Okay, but the learning objective here is to learn what is meant by capacitance and how capacitors store energy. And again, this first little bit, chapter 2, a lot of it is kind of reviewing concepts at a higher level than what we learned in 183. So you could go back if you wanted to and read some of the material in the 183 book, or look at at least the slides that I posted on Canvas if you wanted to just get a little review of this stuff before hearing it at this level. Let's think about a capacitor. Okay, I want you guys to remember that charged or not, our conductors are equipotential. Okay, so remember, as long as there's not a change in the electric field in a conductor, which there can't be because the electric field is zero, then they have to be at the same potential, because if there was a change in the potential, a gradient of the potential, there would be an electric field. Okay, so for the last lecture I did about electrical shielding, the only example of inside those conductors where it wasn't equal potential is when we actually put a charge inside the conductor. Even if it's a hollow conductor with a zero electric field inside, that whole space is at the same potential. Okay, so what this means is they have the same potential or voltage, however you want to describe it, same thing, okay, throughout. Okay, let's go ahead and draw a simple capacitor. Not a simple one, actually, a more complicated one than you normally deal with, a general capacitor. So I'm going to have two funky conductors. Okay, and they're funky just because they're weird shape. All right, so I've got this one. This one's got a charge of positive Q, so it is at a positive voltage, and the one next to it has the same amount of charge, but it's negative Q, and it is at a negative voltage. Okay, and if I wanted to describe the electric field between them, it would be complicated because, again, it's going to be depending on the charge, surface charge density, perpendicular to the surface everywhere. It would be hard to draw. Okay, so the electric field is complicated, but because the potential between throughout the conductor is the same, the difference in potential is relatively simple. Okay, so that's what we're going to try to come up with, a simple way to actually describe the difference in potential, which is related to the electric field of these two funky charge objects, which make up what's called a capacitor. Okay, so we're going to argue that the charge on a conductor is proportional to the electric field, in particular the magnitude of the electric field. Okay, and why is that? Well, I can make two different arguments. The first involves Gauss's law. Okay, so Gauss's law tells me that the closed surface integral of the electric field around a Gaussian surface is going to be equal to the enclosed charge divided by epsilon naught. Okay, if I assume that the electric field, when I change the charge over here, if I assume that it doesn't actually change the direction, okay, which basically means the charge is distributed in the same way. Okay, so charge is distributed and there's no reason to think it wouldn't be basically it's still going to spread out in the same way to cancel each other out. Just if there's less charge, there's going to be, the strength of the force is going to be smaller, but it will all be proportional. Okay, so this equation says as long as I can assume that the charge is driven the same way, the electric field won't change directions, it'll just change strength. So that means if I double Q on a conductor, I will double, that'll double the enclosed charge, and that will double the electric field felt at the surface of my Gaussian surface. All right, so that's one mathematical argument. The other one just comes from direct integration, and it's similar. Okay, so if I use direct integration to calculate the electric field, then I'm going to take the volume integral over the charge density, right, divided by our separation vector, times our r hat here. And again, I'm going to assume that the charge will distribute the same way. I don't really want to write clearly. If I change Q, so that means rho, for example, if I double Q, the charge, the way that it's distributed won't be different, but the charge density overall will also double. Okay, I'll just get more charge per volume in each place. And if I double rho, then my electric field will also, okay, double everywhere. All right, so based on that argument, I have this idea that the electric field is going to be proportional to Q, which, remember, this is the charge on the conductors. Okay, I also know that our change in voltage is also proportional to this line integral of the electric field dotted along some line. Okay, if I put the two together, right, then I know that our change in potential, or the difference in potential between these two conductors, is also proportional to the charge on them. So if I were to measure the change in potential here, it would be proportional to the amount of charge that I place, this one positive and this one negative, on each conductor. Okay, so that's how it works out. So based on this, we can create a new quantity that describes, and maybe the best way to think about it is, if I have a certain delta V, it's actually 1 over C times Q. So C is going to be our capacitance here. Okay, for a given delta V, this will tell me how much charge is on each of the capacitors. It's going to be 1 over C, this is our proportionality constant, times Q. Okay, or I can rewrite that. The more common way to write that is the capacitance is equal to Q divided by delta V. Okay, but again, this is our constant of proportionality that relates the voltage difference between two conductors, okay, to the amount of charge I put on the conductor. All right, so the more charge it is, the bigger the difference in voltage is going to be. This value here tells me for any type of conductor, any shape, any funkiness, which could cause a lot of complications with the electric field, but not so much with the change in voltage, this capacitance here will describe that proportionality. Let's do some examples to actually further describe how we can define what capacitance means. Okay, so here I'm saying it's just a proportionality constant, but really, of course, this proportionality constant, it can't be the same for any type of conductor. It has to change for different types of conductors that we can design. Example 1, will be parallel plate capacitor. Okay, so parallel plate capacitor, I'm going to have a positively charged plate here. Okay, and below that I'll put a negatively charged plate. Okay, we're going to charge these guys up to the same charge by hooking them up to some reservoir of charge like a battery or something like that, and then we're going to disconnect them. Okay, and I can show you guys the FET sim just to kind of remind you of how that happens. These two plates, they're going to be separated here by a distance d, and I'm going to draw the electric field of these two plates. The electric field of the top plate is going to point down. And actually, I'm going to draw that a little bit better. I'm going to draw that to go all the way down, and I'll describe why in a second. Okay, so the electric field between them is going to point down. Of course, it's going to point in the direction a positive charge would flow, so that's away from the positive plate and towards the negative plate. Above the positive plate, that electric field is going to point straight up, and it's also going to point up below the negative plate because, again, that is the direction that a positive charge would accelerate in that field. Okay, the actual magnitudes of the electric field above here, the magnitude of the electric field is going to be what's given by if we're far away from the edge of the plate, which I'm not writing this as far away, but that's okay. We'll do a little arrow here. Okay, it's going to be sigma over 2 epsilon naught. Okay, down here, same thing. The magnitude of the electric field is going to be sigma over 2 epsilon naught. That's what we get for our long plates of uniform charge. In between, we got a superposition of those two fields. That's actually going to double the strength of the electric field. So we're just going to get sigma over epsilon naught because we are superimposing the electric field, which is going to point downward from this negative plate, and the downward electric field from the positive plate. Okay, so this is a superposition, which is going to give us, again, 2 times the strength of the field that we get above and below our plates. Okay, so inside, we have an electric field that is equal to sigma over epsilon naught, okay, down. All right. If I wanted to calculate the change in potential, okay, I can still use this equation here that tells me that the potential between the two plates, so starting at 0 and going to D. So I'm actually going to draw a little coordinate system here. This will be the Z direction. This is going to be 0 here. Okay, I'm going to do that line integral of the electric field in the Z direction. That's going to be sigma over epsilon naught, but it's negative, okay, because it's downward. I also have this negative sign here. Okay, that just comes out of the equation. And in this case, I'm going to integrate in the Z direction. So when I do that, I'm going to get a change in potential that is equal to sigma over epsilon naught times D. So that basically says if I were to draw equipotential lines, the potential is changing linearly in between these two plates. So I would draw them with equal spacing, or if I were to draw my voltage versus distance, it would be a straight line, okay? The electric field would be a horizontal line, voltage would be a straight line up. Okay, that should be reviewed from 183. Again, if you guys need to review it, that's okay. All right, so I know that my delta V is also, if I look, this is the same thing as the magnitude of E, right? So delta V is also equal to E times D, which is, again, sigma over epsilon naught times D, which if I actually put in what epsilon, or what sigma is, I get 1 over epsilon naught Q divided by A this is, right, my sigma times D. All right, let's keep going. I know that Q divided by my voltage is equal to C, so that tells me that C is equal to epsilon naught A divided by D. Okay, so what does this tell us? Well, we could think about it. This tells us that if I have a bigger plate, so more area, I get more capacitance. Okay, so what does it mean to have more capacitance? Well, that means if I look here at this equation or this equation here, if I have more capacitance, that means for the same amount of charge, I'm getting a smaller change in the potential. Okay, so if the plates are bigger and I don't put more charge on them, I'm going to get a smaller difference in potential between the plates. All right, what if I have a smaller distance? So if I shrink D, okay, again, I'm going to get more capacitance, okay? So if I shrink the distance between them, but I don't change Q here, I'm going to get a bigger C. I'm not changing Q. That's going to decrease the amount of electric potential between them. Okay, but again, what I want you guys to notice here is I can learn something from the capacitance in terms of how the charge on the plate is related to the change in voltage between the two plates. All right, let's do another example. So let me see here. Our example 2 will be a spherical conductor. And what this is going to look like is a sphere inside here. The inside sphere is going to have a radius. Let me draw it a little bigger. Let's see. We're going to have an inside sphere here. It's going to have a radius A. Our outside sphere here is going to have a radius of B. We'll make the inside sphere here have a positive charge of Q, and our outside sphere, or shell really, will have a negative charge of Q. Okay, now let's think about the capacitance in this case. So the electric field is going to be given by 1 over 4 pi epsilon naught Q, the charge sphere, divided by r squared, r hat. Okay, I can integrate again to find the potential difference between them. In this case, I'm going to integrate from B to A. And I'm going to be integrating that electric field in the r direction. Okay, so I'm basically going to do the integral from the outside in here. Okay, when I plug in that electric field, again, the dot product is going to go away because r hat and dr are in the same direction. So I'm going to end up with, let me actually pull out all the constants. Negative Q over 4 pi epsilon naught, and then the integral from A to B of 1 over r squared dr. When I take that integral, the negative sign is going to go away. I'm going to get another negative, and this is going to be 1 over r from A to B. So I get that my difference in potential is Q over 4 pi epsilon naught, 1 over A. Let me write that again. 1 over A minus 1 over B. Okay. And if I did a little bit of extra math here, I can figure out, therefore, that the capacitance is equal to Q, right, divided by delta V, and that's going to be 4 pi epsilon naught A times B divided by B minus A. Okay, so that's a little bit more complicated than what I had before in terms of understanding how the potential changes when I change the radius of my two spheres, okay? But I want you guys to note, in either case, the capacitance depends only on our epsilon naught, which is our permittivity of free space, right? That constant, and the geometry, which is to say that this proportionality constant, C, that tells us how the change in potential is related to the charge on the spheres, C, what really determines that proportionality constant has to do with the geometry of the capacitor that we set up. In this case, it has to do with the area of the plates and the distance between them. And in this case, again, it has to also do with the size of the plates, which can be described by their radiuses and the distance between the two spheres. Okay, so that's pretty interesting. So if I want to design a capacitor that has a particular relationship, particular delta V for a certain amount of charge accumulated, I'm going to monkey around with the geometry until I get what I want.